In this demo, we show a new side-channel attack that allows any smartphone applications to eavesdrop on the user's phone call without the requirement of any sensitive user permissions. As we all know, modern smartphones use permissions to protect user privacy. For sensitive sensors that may leak the user's private information, smartphone applications will not be able to collect their data without the user's permission. In this demo, we show that the zero-permission accelerometer can also be used to collect sensitive user information. It allows smartphone applications to eavesdrop on the user's phone call freely. The basic idea is that when a smartphone plays an audio signal through its loudspeaker, the vibration will reach the accelerometer through the shared board and have a significant impact on the accelerometer measurements. Therefore, an adversary who wants to eavesdrop on the user's phone call can collect accelerometer measurements in the background and then use deep learning models to extract speech information from collected signals. We now present our experimental validations to demonstrate the feasibility of this attack. For illustration, we play an audio signal through the smartphone speaker and collect motion sensor data in the background. We can see that the accelerometer signal has a very similar structure to the audio signal, indicating that the accelerometer has successfully captured a significant amount of the voice signal. The effectiveness of the attack is also determined by the sampling rate of the accelerometer. According to the literature, the typical fundamental frequency for an adult male and adult female respectively lie in the range of 85 to 180 Hz and 165 to 255 Hz. For accelerometers, their sampling rate is mainly determined by the hardware of the smartphone. According to our experimental results, accelerometers on recent smartphones can already achieve a sampling rate of 500 Hz. This means that the sensor can reproduce the frequency components up to 250 Hz, which almost covers the entire fundamental frequency band of adult speech. Here, a figure plots the sampling rates of 9 smartphones released in different years. We can see that the sampling rate of the accelerometer increases rapidly with the development of smartphone models. The threat of motion sensors to speech privacy has become a serious issue and will continue to grow due to the rapid improvement of smartphone models. Now, let's look at the robustness of this attack. Human activities can significantly affect the measurements of smartphone accelerometers, and thus might be able to distort the speech information inferred by the adversary. To evaluate the robustness of this attack, we conduct experiments to evaluate the impact of 5 different human activities, including walking, ascending and descending stairs, standing up and sitting down, waving hands and typing messages. This figure shows the scalegram of the collected accelerometer readings. We can see that the tested activities rarely affect frequency components above 80 Hz. And for human speech, the fundamental frequency typically starts from 85 Hz. Therefore, we can use a high-pass filter to eliminate significant distortions caused by human activities. Based on the above observations, we implemented a deep learning-based system that could recognize and even reconstruct the speech signal played by the smartphone speaker. The system has 3 components: pre-processing, speech recognition, and speech reconstruction. The pre-processing part reduces the noise of the acceleration signal and converts the signal into spectrogram representations. Speech recognition converts spectrograms to text. It allows the adversary to recognize pre-trained numbers, letters, and hot words from the accelerometer measurements. Speech reconstruction restores voice signals from acceleration spectrograms. It allows the adversary to double-check the recognition results with human ears. We now use a real signal to illustrate the process of speech recognition. Given an accelerometer signal, we first use a high-pass filter to eliminate significant distortions caused by gravity and human activities. We then convert the signal to its spectrogram representation and cut the spectrogram into multiple short segments, each of which corresponds to a single word. Finally, we use our recognition model to convert spectrograms to text. To evaluate the effectiveness of the recognition model, we first trained a model that can recognize keywords and the speaker from the accelerometer readings. During the evaluation, we play a series of speech signals on the smartphone and collect accelerometer readings through a third-party Android application running in the background. We then use the accelerometer measurements to predict the voice signal played by the smartphone speaker. We can see that our model achieves 78% accuracy in recognizing 10 digits and 55% accuracy in recognizing 10 digits plus 26 letters. It can also achieve 70% accuracy on recognizing 20 speakers. The recognition model can also be used to search hot words from sentences. In this experiment, we trained a hot word search model that can distinguish between 8 hot words and other insensitive words. We collect 200 short sentences from 4 speakers and use the model to locate and identify pre-trained hot words from the sentences. As shown in the table, our recognition model can achieve over 90% recognition accuracy, averagely on those 8 hot words. The accuracy is slightly higher than the recognition accuracy on the 10 digits. This is because the spectrograms of these 8 hot words are more distinctive in comparison with digits and letters. For speech reconstruction, given an accelerometer signal, we first use a high-pass filter to eliminate significant distortions, and then convert the signal to its spectrogram representation. After that, we use our reconstruction model to convert the accelerometer spectrogram to the corresponding audio spectrogram. Finally, we use the Griffin-Lim or GL algorithm to recover the audio signal from the audio spectrogram. Now, let's listen to some reconstructed examples.
Audio 1, 2, 3.
You can hear that most structures and details are roughly recovered. The reason why the reconstructed signals are not very clear is because the consonant information is mainly distributed in the high-frequency domain and thus cannot be recovered. Here is the conclusion of our demo. First, sound signals emitted by smartphone speakers can significantly affect the accelerometer on the same smartphone. Second, accelerometers on recent smartphones almost cover the entire fundamental frequency band of adult speech. Third, using deep learning techniques, it is possible to recognize and reconstruct the speech signals from the accelerometer measurements.